All right, let's talk about three words you've probably heard a million times: work, energy, and power. But we're not going to do this in that boring high school physics kind of way. Nope. We're going to look at these as the actual rules of the universe, the code that runs everything from a planet orbiting the sun to the phone in your hand. And it all starts with one simple, unbreakable rule. So let me just ask you a question, and it's a big one. Think about all the energy that's around us right now. The light from your screen, the heat in the room, the very electrical signals firing in your brain that let you understand my voice. All of that is energy. But can it ever just vanish? Can it be completely wiped out of existence? The answer is a hard no. And that's not just a guideline or a good idea. It is a fundamental, non-negotiable law of reality. And if you can really wrap your head around this one single fact, everything else we're about to discuss is going to click into place. Now, this ironclad rule has a name, of course. It's called the law of conservation of energy. But I think a better way to think about it is like the universe's ultimate golden rule. It's the most important accounting principle in all of existence. What this really means is that the total amount of energy in the universe has been and always will be exactly the same. It's a closed system. You can't just make new energy out of thin air, and you can't get rid of it. All you can do is change its costume, like the electrical energy from the wall becomes light and heat in a lamp, or you can pass it from one thing to another. So if we're saying energy is like this universal currency that just gets passed around, what does it actually look like? Well, it shows up in a ton of different forms, but for our purposes, when we're talking about how things move and interact, we really only need to focus on two main types. These are the two key players in the game. On one hand, you've got kinetic energy. This is the energy of motion. Think of it as cash in your pocket, ready to be spent right now. And on the other hand, you've got potential energy. This is energy that's been stored up, just waiting for the right moment. It's kind of like money you've got sitting in a savings account. So let's look a little closer at kinetic energy. The formula shows it depends on two things: the object's mass and its velocity, or speed. But here's the kicker, the part you really need to see. The velocity is squared. That is a huge deal. It means if you double an object's speed, you don't just double its energy, you quadruple it. This is why a tiny little bullet moving incredibly fast can have way more destructive energy than a big bowling ball rolling slowly. It's all about that speed. And then there's potential energy. This is the what-if energy. The energy something has because of its position or its state. The easiest way to picture this is just holding a tennis ball up in the air. Right now, it's not moving. But by lifting it up against gravity, you've packed it full of stored energy. It has the potential to do something. It's just waiting. And here is where it all comes together. The second you let go of that ball, that savings account of potential energy starts cashing out. It converts moment by moment into kinetic energy, the energy of motion. As it falls, its potential energy drops and its kinetic energy skyrockets, making it go faster and faster. The universe keeps perfect books. Every bit of potential energy it loses, it gains as kinetic energy. The total amount never changes. Okay, so energy is conserved and it can swap between potential and kinetic. But how does it actually get from one place to another? How do you give a bowling ball kinetic energy in the first place? Well, the physical mechanism for transferring energy is called work. Now, in physics, work has a very, very specific meaning. It's not about how tired you feel or how hard you tried. It is the literal, measurable process of transferring energy from one system to another by applying a force. And for work to actually happen, three conditions have to be met. 1, you need a force, a simple push or a pull. 2, you need displacement. The object has to actually move. And 3, this is the one people forget, the movement has to be in the direction of the force. So if you spend all day pushing on a solid brick wall, you'll get exhausted, right? But since the wall didn't move in the world of physics, you've done absolutely zero work on it. No energy was transferred. So that's the big takeaway here. When we talk about work in our everyday lives, we mean effort. But in physics, work is the official transaction receipt. It's the proof that energy has changed hands. So now we have our two big ideas on the table. We've got energy and we've got work, which is the way we move that energy around. Let's connect them with one of the most powerful and useful theorems in all of physics. It's called the Work-Energy Theorem, and it's so beautifully simple. It just says that the total amount of work you do on an object is exactly equal to the change in that object's kinetic energy. It's the receipt, remember? The work you put in is the motion you get out. Let's go back to that shopping cart. As you push it down the aisle, the work you're doing with your arms is being directly converted into the cart's kinetic energy, which is why it speeds up. If you do 10 joules of work, the cart gains exactly 10 joules of kinetic energy. It's a perfect one-to-one exchange. All right, there's just one last piece to this whole puzzle, and it's called power. Because let's be honest, sometimes it's not just about how much work you do, but how fast you can get it done. And to make this all feel real, we're going to look at a super practical example from the source material, mowing the lawn. So power is just the rate at which you do work. Let's say you have to lift a heavy box onto a shelf. That requires a certain amount of work, right? Well, lifting it in 2 seconds requires a lot more power than lifting it over, say, 20 seconds. Same work, different power. But what's really wild is when you start to look at how little energy some of these everyday tasks actually require. Okay, back to the lawnmower. According to the calculations, pushing that mower across the lawn requires about 1,536 joules of work. Now, a joule is the standard unit of energy. And, well, 1,500 of anything sounds like a pretty decent amount, doesn't it? But what happens when we translate that into a unit we all understand? Food calories. That 1,536 joules of physical work, it's the equivalent of just 0.367 food calories. That's not even 1 calorie. It's less than half of one. This right here puts it all into perspective. Look at that tiny, almost invisible sliver of energy from mowing the lawn compared to what an average person might eat in a day. It's a stunning reminder that most of the energy we consume isn't for doing work, like pushing things. It's for the incredible, hidden work of just keeping our bodies warm, our hearts beating, and our brains running. And that kind of leaves us with one last big question. If the physical work of an everyday chore is just a tiny fraction of a single food calorie, what does that say about the mind-boggling amount of energy it takes to do the real work of our civilization? To power entire cities, to launch rockets into space, to run the internet. The same laws of work, energy, and power apply, but on a scale that is truly awesome to comprehend.